7.3 is about special right triangles. We have two types of special right triangles. There's a 45-45-90 triangle because it has a 45-degree angle, another 45-degree angle, and a 90-degree angle. Those are not subtraction signs, they are dashes. And then we also have a 30-60-90 triangle. So a 30-degree, 60-degree, and 90-degree angle inside of the triangle. The reason we call them special right triangles is because their sides have a specific ratio, and this ratio allows us to solve for all the sides of the triangle. Back in 7.2, we used Pythagorean theorem to solve for the sides of a triangle, but you had to know two sides in order to solve for the third. In special right triangles, you only need one side, and then you can solve for all the other sides with just that one side.
Please excuse the interruption, but the hall sweep is over.
The ratio for 45-45-90 is 1 to 1 to square root of 2, which means we have two congruent sides. The ratio for a 30-60-90 triangle is 1 to square root of 3 to 2. What the triangles are going to look like for 45-45-90 is like this. So across from our 45-degree angles, we can put n. Across from the 90-degree angle, we can put n times the square root of 2. What this means is that these sides are equal to each other, and this side is exactly square root 2 times bigger than these sides. For a 30-60-90 triangle, it's going to look like this. So across from 30 degrees, we always have n. Across from 60 degrees, we always have n times the square root of 3. And across from 90 degrees, we have 2n. Okay, 30 degrees is our smallest angle, so across from it is going to be our smallest side. Then we have 60 degrees. Across from 60 degrees is n times the square root of 3, which means that that side, this side, is exactly square root 3 times bigger than our shorter side, than this one. And then lastly, across from our 90-degree angle, we have 2n, which means that this side is exactly twice as big as our smallest side. Okay, let's look at some examples of how we use these triangles to help us solve for the sides. Here's our first example. We're going to take a look at 30-60-90 triangles first. Okay, I've labeled one side with 5 and the other sides with x and y. That's what we're trying to solve for. We're going to use the triangle with the ends, this one, and put ends on our own triangle to help us figure it out. So what I mean is across from 30 degrees is always n, which means 5 is equal to n. Across from 60 degrees is always n times the square root of 3. So x is equal to n times the square root of 3. Across from 90 degrees is 2n, so y is equal to 2n. The first step for these problems is normally solve for n. The second step is take that and plug it in. Well, we already have what n equals. We didn't have to solve anything. We have n equals 5. The last thing that we need to do then is just take it and plug it in to figure out what x and y are equal to. So here, y is going to be equal to 2 times 5, which is equal to 10. Over here, x is going to be equal to 5 times the square root of 3. Let's try another example. In this example, I've labeled the side across from 30 x, the side across from 60 4 times the square root of 3, and the side across from 90 y. We still want to start out by labeling our own triangle with the ends. So across from 30 should be n, across from 60 should be n times the square root of 3, and across from 90 is 2n. We're going to have to use this equation, n times the square root of 3 is equal to 4 times the square root of 3, to solve for n. The square root of 3 is attached to the n by multiplication. To undo multiplication, you want to divide. So we divide both sides by the square root of 3. On the left side, it cancels out, and it also happens to cancel out on the right side. What that leaves us with is n is equal to 4. The last step is to take that and plug it back in to find x and y. So here, x is equal to 4, and y is equal to 2 times 4, which is equal to 8.